Combinations, like permutations, are used for counting in cases where selection occurs without replacement. But in this case, the order does not matter, unlike permutations, where the order of those selections is important. In order to drive towards a formula for combinations, we actually want to start off by considering a case where order does matter. We want to list all the ordered selections of two numbers from the list of numbers 1, 2, and 3. We could come up with 1 and 2, 1 and 3, 2 and 1, 2 and 3, 3 and 1, and 3 and 2 as all of those pairs. So we come up with 6 different possibilities, which makes sense because if we calculated permutations with n equal to 3 and r equal to 2, this would give us 3 factorial all over 3 minus 2 factorial, or 6. Again, since we're driving towards a definition for combinations, now we want to update this to look at the unordered results. If we're looking at unordered results, now we can throw out 2 and 1 because we already have 1 and 2. Similarly, we can throw out 3 and 1 because we have 1 and 3. And we can throw out 3 and 2 because we have 2 and 3. In this case, what we've done is taken our 6 different results and cut that in half. To make this a little bit more complicated, we could say that's the same as dividing this by 2 factorial, because that would be 6 divided by 2 times 1, giving us 3 results. And that's what we're going to look at to generalize and come up with this formula for combinations. So lowercase n, capital C, lowercase r will be our notation for combinations. And this formula will be exactly the same as our formula for permutations. But in the denominator, we're going to introduce r factorial, which is that 2 factorial from our order up above, or from our example up above. In Desmos, we'll plug that in as NCR with a capital C, and then again using function notation, we'll feed in values for n, the size of the group we're selecting from, and r, the number of selections. We can apply this to games, for instance in the board game Clue, which uses a deck of 21 cards. 3 cards are set aside as part of the solution after all the cards are dealt for the murder mystery. Then if 3 people are playing, that means each person gets a third of the 18 cards that aren't part of that solution. So each person gets 6 cards in their hand. How many different 6-card hands are possible? This would be a case for combinations, since no 2 people can get the same card. The same card can't be dealt twice. We know selection is occurring without replacement. And order doesn't matter, because it doesn't matter what order you get your cards in. You can move them around in your hand. It's irrelevant. So out of 21 cards, how many ways can we get a hand with 6 cards? In Desmos, we literally have NCR typed in with a capital C, and we'll type in 21, 6 to get 54,264 possible combinations. In example 5, we have a non-profit organization consisting of 20 members that will form a sub-team of 4 members to look over and review their budget. In part A, how many different sub-teams of 4 are possible, assuming all of the duties are shared equally? This is different than the example we had with permutations because now they aren't officers, just 4 people being selected for a team. Doesn't matter if you're selected first, last, or somewhere in between. So this is a case for combinations where out of 20 people, we'll be selecting 4. So we'll update that to 20, 4 to get 4,845 different possible combinations. In part B, we have a similar scenario, but now one of those team members will be chosen to lead the subteam. This becomes a case for combining combinations with the multiplication rule for counting. The multiplication rule tells us to list the number of possibilities for the first event times the number of possibilities for the second event, and so on. Multiplying those together gives us the total number of possibilities. So for the first selection, we need to choose one person out of this team. So out of 20, we'll select one person to be the leader, and then we'll need to multiply that by our remaining selections. Now we only have 19 people remaining and only 3 spots left to fill on the team. To calculate this in Desmos, we'll literally just multiply another combination, where in the first one we have 20, 1, and the second one will have 19, 3, to get 19,380 possible combinations for this scenario.